Hi everyone, and thanks for tuning in again. We're going to talk about the process of Gauss-Jordan elimination to solve a system. That's pretty hard too, I heard. But what's this reduced row echelon form thing? Once again, I'm going to use a couple of nice examples and explain everything step by step. Before you continue watching this, please make sure you've seen our Gaussian elimination with back substitution presentation first. It's pretty awesome. I think you'd like it. So with no more delays, let's get into it. So let's take a look at our first example. So I'm actually going to cheat and be a little bit naughty and use my example 1 from our presentation on Gaussian elimination and use it for our Gauss-Jordan elimination question. So if you watch that first presentation, you should know that we start with an augmented matrix. We follow through with a process called Gaussian elimination, in which we are allowed to use 3 strategies to then proceed and find something called the row echelon form, which is this 1, 0, 1 format. But Gauss-Jordan elimination is Gaussian elimination, but continued with an extra step or 2 down the bottom. We continue from row echelon form and use our leading ones to create zeros above and below these leading ones on the left side of this matrix. And once we get there, the matrix is said to be in reduced row echelon form. Let's just take a look at what that process will look like. It continues from row echelon form. We use this 1 to turn this number above it into a 0, like so. And that is actually it. Once we are at this 1, 0, 0, 1 format, we have finished the Gauss-Jordan elimination process. And we have reached reduced row echelon form. Let's give that a try. We've already got our 0 here, so actually all we need to do is to turn this -4 into a 0 as well, and we are finished. So in this case, the second row is not going to change. Let's write that first. We now want to use this leading 1 to turn this -4 into a 0. So we're going to add a multiple of one row to another. What will that be this time? Did you figure it out? Here it is. We're going to multiply the second row by 4 and add it to the first row. Let's write that over there. And let's give it a try. 4 times this, 0. Plus this, 1. 4 times this, 4. Plus -4 gives 0, as we wanted. 4 times -1 gives -4. -4 plus 6, 2. So this Gauss-Jordan elimination process is now finished. And this final form is called reduced row echelon form. Reduced row echelon form has this format of 1, 0, 0, 1 on the left side. And this is very important. Let's just have a brief talk about that. This is actually called the identity matrix. Right there we have the numbers 1, 0, 0, 1. So to make it a matrix, we actually have to put our square brackets, like so. An identity matrix must be a square matrix. In other words, it must have the same number of rows and columns. In this case, we have a 2 by 2 square matrix. Why is it called an identity matrix? That's a discussion for another time. Every identity matrix has a main diagonal, starting from the top left down to the bottom right. And all entries in that main diagonal are 1s. These 1s are actually the leading ones from the Gaussian elimination process. Every other entry in the matrix must be a 0. So here we have 1s in the main diagonal and all other entries are 0s. An identity matrix can be symbolized by the letter capital I. Identity matrices don't always have to be 2 by 2. They could also be 3 by 3, and they can get as big as you like, as long as they are square matrices. So once again, you can see we have a main diagonal consisting of only 1s, and every other entry in the matrix is a 0, the 3 by 3 identity matrix. This situation here, we have 2 different identity matrices because they are different orders. So actually, calling them both I is a little bit inappropriate. If this situation ever happens, to distinguish between the 2, you can call the 2 by 2 identity matrix I2. And the 3 by 3 identity matrix I3. That's enough about identity matrices for now. Let's go back and finish off example 1. Once we get to here again, we take this and write it as a system of equations. Let's try it. This first row will give us the equation x plus 0 equals 2, telling us that x is 2. And this second row down here gives us the equation 0 plus y equals -1, which is super easy, right? We're simply just reading the answers of this final matrix down here to give us our solution. Again, you can just highlight your x and y value right here, or you can be fancy and write it as a point or ordered pair, the point to -1. So in summing up, we started with this augmented matrix, we ended up at reduced row echelon form, and the process we carried out is called Gauss-Jordan elimination. Before we move on to example 2, we're just going to stop for a minute and look at a special way to view the original question. This is not essential to know for Gauss-Jordan elimination, but if you are studying matrices at this level, there is no doubt you're going to be seeing it pretty soon. So we might as well just stop and take a quick look, eh? It'll only take a minute. Here is the original question as we had before. These two equations can be written in another matrix form like this. We have a 2x1 matrix equaling another 2x1 matrix. For the left matrix, there will be two entries, 2x minus y and x minus 4y. And the right matrix will also have two entries, 5 and 6. These come from the original two equations, from there and from there. It simply says that this equals this, which is the first equation, and this equals this, which is the second equation. And of course, these two matrices can be equal because they have the same order. We can now do another step, and the matrix on the left can actually be factored into a matrix product, like this. Can you see that? This matrix times this matrix equals this matrix? I hope you haven't forgotten how to do matrix multiplication now. Take a while to look at this and convince yourself that this makes sense. Remember, matrix multiplication, this number and this number need to match, which they do, and the resulting matrix will be this by this, a 2x1 matrix, which is what we had in the previous step. So doing the matrix multiplication and going backwards just to check it, we would get 2 times x plus -1 times y, which is this, equaling 5, which is up here. And then we would get 1 times x plus -4 times y, which is that, which in turn equals 6 over here, giving this. Why am I showing you this? Because these three matrices here, 1, 2, and 3, have a very special meaning when solving systems of equations using matrices. This first matrix here is usually denoted by a capital A, like that, and it is called the coefficient matrix because it represents the coefficients of the variables in the original equations. This second matrix here is usually denoted by a capital X, and it means the matrix of variables. It contains the x and the y, which is what we're trying to solve for in the original system of equations. And this third matrix is called the matrix of constants, because it contains the two constants, which are the 5 and the 6 in our original equations here. So what is the significance of this? Every system of equation can be written in matrix form and then written as this matrix equation. Matrix A times matrix X equals matrix B. And from that point, the goal is always to solve for this matrix X. Once we have found the matrix X, that means we know the values of X and the values of Y, and we have solved the original equations. Not only does this work for a 2x2 system, it could work for a 3x3 system, and actually any number of variables you like. Phew! Now let's go back to our example. Wow, that's pretty awesome, right? Complicated, but very important. So why did I go into the process of explaining the identity matrix and the matrices A, X, and B to you? I wanted to describe Gauss-Jordan elimination to you in one final way. We started with the augmented matrix, right? A way we can describe the augmented matrix is like this. Does that make sense? The left side is simply the coefficient matrix, given by this, right? And the right side is simply the matrix of constants, right? Given by this. And we end up down here at something called the reduced row echelon form. Another way to describe the reduced row echelon form is like this. Does that make sense? The left side of the reduced row echelon form is simply the identity matrix, right here. And the right side is simply the matrix of variables, given by this. So when written in reduced row echelon form, we can simply just read off the solutions, the values for x and y. So there you have it, everyone, Gauss-Jordan elimination for a 2x2 system. Let's try something a little bit trickier. And this will be our second example. But guess what? I'm going to cheat again. We're going to take the same example 2 from our Gaussian elimination with back substitution, 3x3 example, and use it to do Gauss-Jordan elimination. So just like before, we started with our augmented matrix. We did our process of Gaussian elimination using our 3 strategies to end up at row echelon form. But with Gauss-Jordan elimination, we continue from here for a couple more steps to get to our reduced row echelon form. Here's a quick visual as to what that process will look like. So we start from row echelon form. We now kind of work backwards. We use this final leading one to turn these 2 numbers above it into zeros, like so. And our final step, we use our second leading one to turn the number above that into a 0. And once we are here, we have reached reduced row echelon form, and the Gauss-Jordan elimination process has finished. Now let's go back to the example and give it a try. So again, to get our reduced row echelon form this time, it's actually going to look like this: 1, 0, 0, 0, 1, 0, and 0, 0, 1. That is actually what we're aiming for this time. So the first thing we're going to do is use this leading one here and turn these 2 numbers into zeros. To make this -2 into a 0, let's multiply the third row by 2 and add it to the second row. Like so, let's do it. 2 times that plus that, 0. 2 times that plus that, 1. 2 times that, 2, plus that, 0, which is what we wanted. 2 times that, -6, plus that gives 1. We now want to turn this 3 into a 0. So now let's multiply this by -3 and add it to the first row. Like that, let's do it. -3 times this plus this is 1. -3 times this is 0. Plus -4 leaves -4. -3 times this, -3 plus 3, 0. What we wanted. -3 times this, 9 plus -8 is 1. We are nearly home. We now use this one to turn this -4 above it into a 0 as well. Only the first row is going to change, so I've written the second and third rows down there already because they're not going to change. So to turn this -4 into a 0, let's multiply this by +4, add it to the first row, and that will give 0. Like that, let's do it. 4 times this is 0, plus 1, 1. 4 times this gives 4, plus -4, 0, what we wanted. 4 times 0, 0, plus 0, 0. 4 times 1 is 4, plus 1, 5. So there we have it again, everyone, the process of Gauss-Jordan elimination. Starting with an augmented matrix, ending up at reduced row echelon form, that process is called Gauss-Jordan elimination. Before we go ahead and write our final solution, the x, y, and z, we're just going to stop and look closely at exactly what reduced row echelon form is. Let's take a look. So by now we should be familiar with the 3 criteria for row echelon form. For a matrix to be in reduced row echelon form, it must satisfy all the criteria for row echelon form with one final 4th criteria. And that criteria states, any leading one must be the only non-zero entry in its column. In other words, if I'm a leading one in a matrix and I look up and down at the other numbers in my column, the only numbers I should be able to see are zeros. This must be true for all the leading ones in the matrix. And to explain this criteria, let's take a look at this matrix over here. Is this in reduced row echelon form? What do you think? Let's take a look at the leading ones. So the 4th criteria states that each leading one should only have zeros above or below it. So this leading one has all zeros in its column, except for itself. And the same with this leading one, all zeros above it. This leading one has a 0 below it, but it does not have a 0 above it, it has a -4. So this particular matrix is not in reduced row echelon form. So to fix this, we just need to do one more step. To turn this -4 into a 0, let's multiply the second row by +4 and add it to the first row. Like so, let's do it. 4 times this, 0. Plus this, 1. 4 times this, 4. Plus this, 0. What we wanted. 4 times this, 0. Plus this, 0. 4 times this, negative 24. Plus this, negative 19. If we look at the leading ones now, individually, we can see that they all have zeros above and below them. So this matrix is now in reduced row echelon form. So there we have it, reduced row echelon form, and the 4 criteria that define it. Let's go back and finish our example 2. Once we're in reduced row echelon form, we can simply read off the solutions. Hopefully you can see that x is 5, and y is 1, and z is negative 3. Or if you like, we can write it as the order triple 5, 1, negative 3. And once again, let's close off this example by using what we know about the identity matrix and matrices A, X, and B to once again describe the process of Gauss-Jordan elimination. The augmented matrix can be thought of as a matrix constructed from the coefficient matrix A and the matrix of constants B. And reduced row echelon form can be thought of as a matrix constructed from the identity matrix and the matrix of variables. And again, the advantage of Gauss-Jordan elimination is once we get down to here, we can simply read off our solution for our values of x, y, and z. And I hope you're ready for a little bit more practice, because it is now your turn again. Please try example 3. This time, try solving these two systems using Gauss-Jordan elimination. In part A, you have a 2 by 2 system. Just be careful when you start to avoid fractions in your first step. Remember, we always want to avoid fractions. Were you able to do it without getting any fractions? Really? Be honest now. Don't make me come out there and check you're working. And for part B, you have a 3 by 3 system. A little bit more challenging. 3 by 3. Ooh. Please feel free to leave your answers in the comments. And as always, thanks for watching.